what we're going to be going over here is a quadratic function where we're going to be calculating the eigenvalues and the eigenvectors for this function. But what we're going to be looking at here is how these eigenvalues and eigenvectors are related as far as the calculations. What we're going to be looking at is if we know our eigenvalues here, how would we calculate our eigenvectors, and vice versa here. If we know our eigenvectors, how would we calculate our eigenvalues based on our eigenvectors? Okay, so what we're going to be looking at here is this quadratic function that I'm showing here. And along with this quadratic function, we have some cross terms here. What I mean by cross terms is we have this function x squared, y squared, z squared times some coefficients here. But with the original function here, we got some cross terms, yz, xz, and xy. Multiples of each here. Okay, and what we're looking at here is an ellipsoid. And by taking our eigenvalues or eigenvectors here, we'll take this function and actually we eliminate the cross terms here. And we come up with some new coefficients here for our x, y, and z squareds. Okay, so looking at the ellipsoid here, what we start out with is this ellipsoid here, and I've got a hole cut in the middle here showing our axes here, x, y, and z. But what you can see here with this ellipsoid, they are canted off at a different angle. But what we do here by taking the eigenvalues here and vectors, what we do is we take that function that we had here, we eliminate the cross terms, and we come up with a nice, clean, perpendicular, symmetric function here as a ellipsoid. Now, they're symmetric over here, but they're canted off at different angles. Okay, so what we're going to do here, we'll just look at calculating these eigenvalues and eigenvectors to see where the numbers come from, and then we'll go in and we'll see how they are related here. And really what we're doing here is just an algebraic solution here. So you can see here, just looking at in this terms here with our original function here, you can see how it's canted off here at a different angle. It is symmetric, but it's canted at a different angle. And then we were going to move it over here, and we take our eigenvalues and vectors, and we straighten everything out here. And just to make a point here, this is what we're not going to get into. If we look at our vectors here for our eigenvectors here, you've got some vectors here. They're actually perpendicular to each other for this function that we're looking at here. We're not going to get into the values here, but what you do here by taking those eigenvalues and eigenvectors, you actually rotate these eigenvectors and also the values up into the situation here where they follow this new algebraic solution here, or our straightened out solution here without the cross terms. Okay, so first off, let's go and see where we got our numbers from. Okay, so the first thing you have to do here, you have to set up a square matrix here based on that original quadratic function with the cross terms here. And I'm not going to get into this exactly how you would do it here, just to go over it real quickly, but you're going to have your x, y, z, and 1 columns across the top here representing your columns, and x, y, z here, and also that one term here representing the rows here. And just to show how it would go here, the squared terms sit on the diagonal, so x row here times x column would be x squared, that would be 103. Y, a y column here times y row here, that would be 125. That's the coefficient. You can see y times y here. That's y squared, 125. And z squared here would be row z, column z, coefficient 66. And then we got that lone value here, 294, minus 294. And then the other cross terms, all you have to do is same situation, y, z. Let's go through it real quick here. Y, z, at 60, it's sitting here. So you get half of it goes to the upper triangle, the other half goes to the lower triangle, z, y. Okay, so you get the point here. Then what you're going to do here to solve this, just to understand where it's coming from, you set up identity matrix. Same, we got a 4x4 matrix, so you got an identity matrix here. Ones are across the diagonals, are on the diagonals, all the rest are zeros. And what you do to solve it, you just take your matrix here that you have, your square matrix, and you subtract from it lambda here. This is what we have to solve for. It could be any variable. It's just referred to as lambda times your identity matrix here, that 4x4 matrix. So you subtract that here from your matrix that you've set up here, and you're going to come up with the matrix here where you have that minus lambda in it. And then if you take the determinant of this new matrix what we have set up with the lambdas here, a determinant of it, set it equal to 0, you're going to come up with one unknown polynomial here. It's going to have some lambda squared, lambda to the 4th here. So you factor it out, and that is your eigenvalues here that you have. I'm just showing them real quickly here. And then you just solve for them, and you're going to get your eigenvalues here based on your factored results here. And just for eigenvectors, I'm just calling these out just to show where they have them here. And they come off of, I just use MapleSoft here. They have a function for eigenvalues, eigenvectors. So each column here in our vector represents an eigenvalue here. Okay, so that's where our numbers come from. So now let's go and let's see how these are related here when it comes to eigenvalues and eigenvectors here for our calculations. Okay, we'll look at the first case here where we're going to calculate our eigenvalues where we know our eigenvectors. That is, we do not know what our eigenvalues are, but we do know what our eigenvectors are. So just as a reference, I'm showing the eigenvalues here. But what we do know is our eigenvectors that I'm showing in columnar form here. I got really 3 eigenvectors here. This one was for a single term that we have here. Okay, so what we first have to do, we have to set up an eigenvector matrix. And just taking those eigenvectors here in each of those columns, we set it up in matrix form here. So we have a 4x4 matrix here. So that we've done here. So the next thing we have to do is we have to invert this matrix here that we have. The eigenvector matrix, what we're doing here is we're just taking each of those rows here in this our eigenvector matrix, and we're turning them into columns, so over in the next matrix that we're going to be dealing with. So the first row here becomes the first column here in our inverse matrix here. Second row becomes our second column here. Third row, third column. Fourth row, the fourth column. Okay, so what we have here is a P, our matrix here for eigenvectors here in an inverse form here. And just to understand what we're looking at, I plotted them out here. So looking at our eigenvector matrix, just looking at it here, there's sort of linear here. I did some negative terms on them, but you can see what we're dealing with. And these matrices here that we're using, you can see they're sort of linear here. They're going to change the coordinates here for our quadratic function that we're going to have. These matrices here eliminate those cross terms. Okay, so back to what we're doing here. We take our inverted matrix here, our P inverse here, where the eigenvector matrix here, each of the rows become the column. Now, the next thing we have to do here is we have to have some matrix multiplication here. Okay, so what we're doing here is we're just taking this inverted matrix here, our eigenvectors here in our inverse form here, and we multiply it times that original matrix that we set up here for our quadratic function with those cross terms here. Okay, so just do that multiplication here. P inverse times the eigenvalue matrix, eigenvalue with eigenvalue, or the eigenmatrix here that we have set up for a quadratic function. And what you come up with is the new matrix here, just showing here. And I did plot that out here, looking at it over here. Again, you can see sort of a linear relationship here. Okay, so here's our matrix multiplication here. We took our P inverse matrix times our quadratic function, the original matrix we have here. And what we would do here next is we take a matrix dot product here. What we're going to do is we just take the matrix that we calculated here, the matrix multiplication one that we've done here between our P inverse and our A matrix here, our quadratic function matrix, and we would do a dot product here. So and make the, well, let's understand this here. We take that matrix that we have here, the EV1 here, and we take it a dot product times our original eigenvector matrix. Let's go up and look at it. That's P here, just to make an understanding here. So this is what we're doing here. We're using this original matrix, this eigenvector matrix that we set up here just in columnar form here. We do not use the inverse here. We use this one. Okay, so let's go back and let's do it. Okay, so we take a what they call a dot product here. And I'm doing all this in MapleSoft here. So we take the dot product times that matrix multiplication, dot product times our eigenvector matrix here. And this gives us our new matrix where we have actually solved for our eigenvalues here. And you can see it across the diagonals here. We have eigenvalues, and those match up with, remember, the eigenvalues that we calculated here. So here's the case where we calculated our eigenvalues here, knowing eigenvectors here, and you can see how they match up. There's some minor cross terms in here of just a minor, you just eliminate those because they have virtually no contribution here. They're so small you just eliminate them. Okay, so we've done that here. We've calculated our eigenvalues based on knowing our eigenvectors. Okay, so then the second case here, and just understand what's going on here. This, after we've done that here, you can see our matrix here with our diagonal here is our eigenvalues. You can see those become the new equation here for our quadratic ellipsoid where we straighten it out. And you can see it's real nice and straight here. And we eliminated the cross terms. We've got new coefficients for our x squared, y squared, and z squared axes here. But it's real nice, and it's leveled out, and it gives us a better understanding of this. We get eliminated the cross terms. Those cross terms added very little or nothing really to the relationship here. So we've done that. Okay, so let's go up here and look at the second case here. This is where we're going to calculate our eigenvectors knowing our eigenvalues, just the reverse here. So what you're going to do is you're going to end up with what we like, similar to what we originally used here, a formula that we originally used to calculate our eigenvalues. So what you're going to do here, you're going to set up this matrix. We're going to evaluate it. You plug in your eigenvalue here. Okay, so remember, this is where we know our eigenvalue. We do not know our eigenvector. So you plug in an eigenvalue. Now remember, we had 3 or 4, well actually we had 3 of them in this equation here. You'd have to plug each one of those in. However you do it here with your computer software or whatever, but you'd have to do it for each one of them. I got the first one here was 147, and then we got a 98 and a 49, so we'd have to do that for each of those. And you take that times the identity matrix, and remember that identity matrix here, 4x4 matrix to match our eigenvalue vector matrix here. Diagonals, the one across the diagonals here. Okay, and then what you do is you just subtract from it a. That's our original quadratic matrix that we've been using here. You subtract that from it, you do your evaluation of the matrix here, and you come up with this here. Okay. All right. So I'm just showing this here. And the next thing, you would have to solve this for each of your terms here. So with MapleSoft, I'm just going to make a shortcut here. They have a function called null space here. You just take a null space of this matrix that we have here, the identity matrix times your eigenvalue, and subtract from it your original matrix. And this function here, the null space, is going to give you your x, y, and z terms here, positions here, eigenvectors here, based on the eigenvalue here of 147. Eigenvalue here, 147. So that's the procedure we'd use here. So we've calculated our eigenvector here based on knowing our eigenvalue here. Okay, so that is how we go about doing that. So maybe let's just go and look at one further example here. Now let's look at the case here where we'll take our symmetric square matrix where it's known. This is the matrix that we've been dealing with our quadratic function. And this is where we want to calculate this quadratic function or confirm that our function is correct based on a symmetric matrix here that we're given. Okay, so what you have to do here to calculate the quadratic equation, I've got it shown here, but just say for the purpose here where we wouldn't have this equation and we want to come up with a quick means of calculating the equation here without going through longhand in coming up with a row column multiplications here. So what you're going to do is, again, you set up a vector here. You're going to have a vector here represented by your columns or rows as x, y, and z, and also that one unit here. Okay, so we set up our vector here, and what you do is you take the dot product here of this matrix, your quadratic matrix that we have here, times this vector here we have here. And what it's going to give you is, and we can go look at it here. So we take the dot product of the matrix here and our vector, matrix here and our vector, and we come up with the solution here, the dot product. Now, that is our quadratic function for that particular matrix. And it's just a good way to either check that your quadratic function you're using is correct here, or to save some time rather than go through longhand to determine what that quadratic function is based on knowing the matrix we have that represents the function. Okay, but you'd have to collect some terms here, but we did confirm that it's correct here if we made our comparisons here. So let's just look at it. 103, I'm throwing x times x here. So that would be 103x squared. And then we have 125 times y, 125 times y squared. And then we have 66 z squared here. And then we have to collect our terms for these cross products here. Minus 30yz and then minus 30zy here. That would be represented as minus 60yz here. And it would be the same for the other two here. That 12xz would be, you'd collect here 6xz times minus 6xz here. That equals minus 12xz. And then 48 was the minus 24yx versus, what do we have here? Another 24xy here, minus 48xy, and then we have that minus 254. Okay, so this is just a good way to check your function to see if it's correct, or to save some time here. Just take the dot product of the matrix that you're dealing with here times setting up the vector here, which is either you have to set up the correct vector for your columns or rows. Okay, so that takes care of that. Okay, so just going back and ending it here, we started out with this quadratic function here. And what we did here with this quadratic function, we determined the eigenvalues and eigenvectors in the quadratic function. This is where you eliminated the cross terms. So we don't have any more cross terms, but we did change the coefficients here for your x, y, and z squared terms here. Okay, and just looking at it over here, so here was our original quadratic function here with those cross terms in it. Eliminated those, and we're back to what we're looking at here, x, y, and z axis. Everything squared up real nice here, and again, very symmetric. And then the other thing we'd have to look at is those eigenvectors and eigenvalues here. They're also rotated when you make come up with your new axis here. Those are a separate topic to talk about and see how they are calculated. Okay, so that'll end our discussion.